Welcome back, class. With this video, we're going to be starting our last chapter in General Chemistry 1, Chapter 12, where we're going to talk about what are known as condensed phases, liquids and solids, and the forces that hold those molecules to each other, right, which we call intermolecular forces. Now, at the end of this chapter, we will discuss a little bit on Chapter 13, some specific topics. That chapter deals with solids specifically, but I'm just going to talk about some very basic stuff about solids. And then I will also, I think, post some supplemental videos there that will talk about some selected other topics from Chapter 13. These will be external videos, not ones that I make. And I may put some of that information on the final exam as extra credit. But of course, Chapter 12 and the stuff that I cover in the PowerPoint from Chapter 13 will be covered on the final exam, along with Chapters 10 and 11. So let's get started. So we've already learned about the three states of matter, right? Solids, liquids, and gases, right? And we talked about some of the basic properties of those. We can sort of review some of that stuff here. So if we look specifically at water, right, as an example, right, we're all familiar with the three phases of water and where they exist and when they exist, right? We have gaseous water or steam, we have liquid water, and we have solid water, or what we know as ice. We know they exist at different temperatures, right? So the phase of something will matter depending on what temperature you're at. We also know that those phases have different densities, right? As we've gone through the different chapters, one of the first things we talked about when we talked about gas chapters was that gases have extremely low densities compared to their solid and liquid counterparts. And we can see that here, right? We can see that the density of steam is 5.9 times 10 to the negative 4, where the density of liquid water is very close to 1. Now, solids would typically be more dense than the liquid. Now, I will point out here so that you don't get confused or don't jump to the wrong conclusion, that water is an exception, right? This is not the normal, right? For water, ice is less dense than the liquid form, and this is why ice floats on the surface of water. But for the vast majority of solids, right, the solid is going to be more dense than the liquid. So this is an aberration, right? It has to do with the way ice crystallizes. Now, to go along with that, right, as the density goes up, right, the molar volume, right, goes down, right? And the molar volume is, again, how much volume 1 mole of material would take up. So in a gas, that's going to be a huge amount, right? So for steam, it's about 30 liters, right, would be the molar volume of steam. And for the liquid and the solid, right, it's going to be much less than that. In this case, about 18 to 19 milliliters, right? Notice the units here, right? 30.6 liters, 18 to 19 milliliters, right? So much, much lower molar volume, right? And that's, again, a reflection of in your gaseous phase, right? There's a whole lot of empty space between the molecules, right? They don't really interact. But in a liquid and solid, the molecules are very close together, right? Essentially as close together as they can be, right? So much lower molar volumes. It goes hand in hand to that higher density. Now, if we take a sort of a big picture look at all the phases, right? And again, these should be nothing new here, really, except for the last category. Right? We talk about the densities, we talked about the shape and the volume. Now, what we're going to focus on in this chapter is what's called the intermolecular forces, right? These are the forces that hold the molecules to each other in a sample. So in a gas, as we talked about when we talked about in our chapter on gases, right, those molecules are not really held together at all. Sometimes we say they don't have any intermolecular forces, right? They don't stick to each other, right, under the kinetic molecular theory. A lot of empty space. Whereas solids and liquids have these intermolecular forces. Now, we might say that in liquid, they're going to be moderate strength. In the solid, they're going to be even stronger, right? And we can see this in how much movement that those phases are allowed, right? Liquids are allowed to move more. That's where their indefinite shape comes from. So those intermolecular forces are not quite as strong. In a solid, where essentially those molecules are locked into place, those intermolecular forces are even stronger. Okay, so as we go through the chapter, we're going to talk about types of intermolecular forces. We're going to talk about different aspects of these intermolecular forces. So what is an intermolecular force? Well, again, it is the forces holding the molecules to each other in our condensed phases, in our liquids and solids. And the structure of those particles, right? So the type of molecule you have will play a role in determining how strong the intermolecular forces will be and the type of intermolecular forces that will be present. Now, all of these particles are attracted to each other by some type of electrostatic force. It really just depends on the form of that electrostatic force or how strong that electrostatic force is. And how strong they are, right, will determine the phase or the state of that matter at a given temperature. So if we consider, say, room temperature, then if a molecule has moderate to strong intermolecular forces, or what we call attractive forces, then those materials will exist as solids and liquids at room temperature. If it has weak intermolecular forces, right, that are easy to break, if you will, right, those materials are likely to exist as a gas at room temperature. So one thing that we can already see is that temperature is going to play a role in intermolecular forces, right? We're going to have to look at temperature as we talk about intermolecular forces. Now, one of the prime properties that we use to sort of compare intermolecular forces is going to be the boiling point. We'll also use the melting point to some extent, but it can get a little bit more complex. There's other factors that get involved. But the boiling point will be one of our go-to properties to look at when we compare intermolecular forces. And the basic idea is the stronger the intermolecular forces, the higher the boiling point will be. Now, if a molecule has really strong intermolecular forces, right, the more resistant to movement they are, right? And so this is why, solids that have really strong intermolecular forces, right, they don't really move. Now, they don't lack movement in the sense that they're totally still, they vibrate, right? And so there is no such thing as a lack of motion. All material will move, has some motion. It just may be vibrational motion. Whereas a liquid, which has a little bit weaker intermolecular forces, right, there's more motion. So now let's jump into talking about the types of intermolecular forces. Before we get to that, let's talk a little bit about these electrostatic ideas. So I said intermolecular forces are based on electrostatic interactions, or essentially, right, the attraction between opposite charges, right? Positive charges attracted to negative charges. And so when we have these, right, in polar molecules, right, so we talk about, when we've talked about molecules, we've spent a lot of time determining in the last chapter or so about whether a molecule is polar or not, right? in a polar molecule, we have what are called dipoles, right? And those dipoles have a positive and a negative end. And so in polar molecules, we're going to see that the positive end of the dipole in one polar molecule will be attracted to the negative end of the dipole in an opposite polar molecule. And we can see that over here with water, where, remember, water has a dipole that looks like this, where we have the positive side of the dipole is, down here by the hydrogens. The negative side of the dipole is up by the oxygen. And so we can see we develop an intermolecular force between the positive end of this molecule and the negative end, or the oxygen, of an adjacent water molecule. And so this is how they're going to develop. Now, what about nonpolar molecules, right? They don't have dipoles, but it turns out even in nonpolar molecules, they're able to develop what we call temporary dipoles, or temporary charge separations. And we'll talk about those in a second. Now, when we think about these attractions, the bigger the charge, the more the attraction. Now, for what that plays for us is if we look at the dipole, right? How polar is the molecule, right? Is this dipole, does it have a large molecular dipole or a smaller molecular dipole, right? The bigger that is, the stronger the attraction is going to be, right? And so your intermolecular forces can be stronger if you have stronger, bigger dipoles in the molecules. It's also going to depend on distance. How close are the molecules to each other, right? The closer they are, the stronger the attraction. The further apart, the bigger they are. Now, where this typically comes into place with us is the size of the molecules, right? Bigger molecules are by necessity going to have to be further apart from each other. So small molecules can typically get closer and they can develop stronger attractions. Now, one thing to keep in mind throughout this chapter when we're talking about intermolecular forces is we will talk about some being very strong, some being very weak, but one thing we have to understand is that they are all small compared to actual chemical bonds, right? So we can see here that, the bond between H&O and water is only about 96 picometers, whereas the intermolecular force is going to have a distance of, a few hundred picometers, right? But any of these intermolecular forces, right, are going to be much, much weaker than an actual bond. Okay. So we got to play that in mind. So when we talk about strong versus weak, we're just comparing it to other intermolecular forces. So there are three fundamental types of intermolecular forces that we can have in a pure substance. So we're going to talk about a total of 4 types, but the 3 that we're going to focus on here first are the types that are present when between pure substances or within substances. So we have what are called dispersion forces, right? These are where we get temporary polarity due to the development of temporary dipoles, right? And those temporary dipoles result from unequal electron distribution in the electron cloud of the molecule. We have dipole-dipole attractions, right? These are the attractions when we have permanent polarity, right? Between the molecular dipole of one molecule and the molecular dipole of another molecule. And then we have a special, what we might call especially strong dipole-dipole attraction when we have certain other atoms bonded to hydrogen. So when hydrogen is attached to a really electronegative atom, it can develop these extra strong dipole-dipole interactions, which we call hydrogen bonds. So let's jump right in to the first one. and those are dispersion forces. So dispersion forces are caused by fluctuations in the electron distribution in the electron cloud of a molecule. So we'll look at some pictures here in a second, but the basic idea is, typically in a molecule, right, we get fairly symmetrical distribution of electrons over the molecule, right, based on, whether it has a dipole or not, but they don't really change a whole lot. But over time, or periodically, let's say, you can develop regions that have excess electron density compared to what it normally would be, and therefore other regions that will have a depleted electron density compared to what it's normal to be. And this allows those areas to develop temporary positive and negative charges, which lead to the formation of a temporary molecular dipole. And this will develop, and then it'll go away. And then it'll develop maybe in a different way within the molecule, and then it'll go away, and so forth. The attractive forces that result from these temporary dipoles are called dispersion forces. These are sometimes called London forces. Now, the key thing with these is that all molecules have them, right? So this is the one type of intermolecular force that is present in every single molecule. Now, the way they work, right, is that one molecule develops this temporary dipole, and then it causes what you might think of as a chain reaction or a cascade, where it induces a temporary dipole to form in the surrounding molecules. And that gives you these connections or these attractions, which we call dispersion forces. So let's look at some pictures to see if we can maybe do a little better job of explaining this. So let's look at this first picture here, where if we could take snapshots of the electron distribution in a molecule or even an atom, right? This is what we might see. So this is a helium atom. You can see it's 2 electrons here. And, we can see we get, electron distribution, fairly spread out. Every so often, you get this kind of setup where the electrons become grouped on one side of the molecule or another, or one side of, in this case, the helium atom or another. And that causes a temporary dipole to develop, where the side with the higher than normal electron distribution gets a partial negative charge, and the side that lacks them will develop a partial positive charge. And this presence, right, can cause a dipole to develop in the adjacent molecule. So if this one is doing this, then that's going to, in this molecule over here on the left, right, it's going to push the electrons away, right? Because the electrons in this molecule, right, are going to want to get away from the electrons here. And so you get a dipole developing here. You get the same kind of thing developing over here. And that gives you these positive and negative partial charges next to each other in adjacent molecules. And these are where we get our dispersion forces, right? So, right, this is the dispersion force, which over time, right, on average, we get enough of these that these forces become strong enough to hold the atoms and or molecules together. Now, maybe very weakly, but it holds them together nonetheless. So, what kinds of things will tell us what molecules might have stronger dispersion forces, while others might have weaker dispersion forces? So, what determines the size of our instantaneous dipole, right? How strong is it? Well, first of all is how easy is this what we call polarizability of the electrons? So this is the charge separation that I was describing in the last slide. How easy does that develop? Well, the easier it's going to be is if you have a big electron cloud. So the bigger the electron cloud, the easier it is to polarize it. Now, what kind of molecules and atoms are going to have big electron clouds? Well, ones with lots of electrons. And if you have larger number of electrons, that means you have more mass, right? So bigger molecules, bigger elements are going to have more electrons, bigger electron clouds, stronger instantaneous dipoles can develop. You're going to get stronger dispersion forces. So the way we might think about this is we get larger molar mass, right? This is sort of our easy way to measure this. We have more electrons. We get a larger electron cloud, which is easier to polarize, which leads to stronger attractions, right? And of course, by the attractions, we mean the dispersion forces. So mass plays a role. So when we talk about strength of dispersion forces, oftentimes we'll compare the molar mass of the molecules. Now, another thing that can play a role is the shape, right? If you have long, skinny molecules, right, they can have more surface contact than more circular or spherically shaped molecules. And so those kinds of molecules are going to have more surface area contact if they're long and skinny, so you can get more area of contact, which gives you bigger dipole, which leads to more dispersion forces. So the shape of the molecule can also play a role here. Okay, so let's look at a couple examples with these effects. So first example over here looks at the noble gases. So in table 12.3 here, we see the series of noble gases, and of course they're going to increase in mass as you go down the periodic table, which means they're going to have larger electron clouds, more electrons, and so we would expect them to have stronger dispersion forces. And that's exactly what we see. Now, again, as I would point out, one of the basic physical properties that we can use to see whether something has stronger dispersion forces is boiling point. And so what we clearly see is the boiling point goes up as you go down here. Now, all of these are, of course, gases. Note this is in Kelvin, not Celsius, so this is still well below 0 Celsius. But what's increasing the boiling point? That means as you go down, you're also increasing the strength of your dispersion forces. And so the bottom line is more molar mass or larger molar mass, higher dispersion force strength. And the stronger those dispersion forces, the higher the boiling point will be. We can also see it in molecules. So this is the series of molecules which are known as hydrocarbons, and we talked about this back when we talked about nomenclature a little bit. And these are just molecules that contain carbon and hydrogen, but as you go to more carbons, right, these molecules get heavier and heavier, and what we see is as molar mass goes up off here to the right, we see that boiling point also goes up. Right? So we get a nice linear increase here. As the mass goes up, the boiling point goes up because the dispersion forces are getting stronger and stronger. Okay, now what about shape? So we can look a little bit at shape here. So these are two versions of the molecule pentane. We have pentane that is a straight chain here, which gives us kind of a long and skinny molecule. And then we have pentane that takes on a different structure. We call it neopentane, but same molecular formula, but it has a more spherical structure, right? All the carbons branch off of one central carbon. And so These more spherical have less area for interaction, so you'd expect less dispersion forces. You would expect a lower boiling point. And that's exactly what we see. So while these molecules are identical in terms of their molar mass and the atoms involved, etc., what you see is we see a much lower boiling point when we get neopentane, right? And of course, this lower boiling point means weaker dispersion forces. So stronger dispersion forces in these long skinny molecules leads to a higher boiling point. Weaker dispersion forces because of the lower contact leads to a lower boiling point because of the weaker dispersion forces. And so this is how shape can play a little bit of a role here. Okay, so let's kind of summarize this whole thing. So the stronger the attractions among the atoms or molecules, the more energy it will take to separate them, right? So the idea is molecules or atoms are held together nice and tight, or nice and stable, strong intermolecular forces, right? So strong dispersion forces if we're arguing, but this we'll be able to apply this to any type of intermolecular force. The more energy it takes to separate them, right? If you have to input more energy, that means it's going to be harder to boil. You're going to have to go to a higher temperature to get to input that energy. And so we're going to result in a higher boiling point, right? Because to boil it, we have to break those intermolecular forces, so we have to put enough energy in to do that. And so the higher the normal boiling point of a liquid, the stronger the intermolecular attractive forces are. So this is one of the big things that we're going to use as we go through and talk about intermolecular forces. Now again, remember, these intermolecular forces are much weaker than actual bonds, and this is why when you boil something, right, you don't break the bonds, you simply break the intermolecular forces, right? All right, so next time, or in the next video, we will talk about the other types of intermolecular forces.